welcome back to my YouTube channel. Today we'll be dealing with N4 engineering science, which is strength, which is we'll be dealing with stress and strain, right? So whereby this topic you'll be dealing with this thing when you get to N5 again. We call this topic strength of material. Until if you're going to take strength of material until N6, you must know this thing permanently, so because they are there. So all right guys, without wasting time guys, if you have not subscribed to my YouTube channel, may you kindly subscribe to my YouTube channel and click the notification button so that you'll be notified whenever I post a new video. So we have given here question 6 says the stress and strain in young modulus. They have given it says there, name the 3 types of stresses. We have given 6 point, says name 3 types of forces. Okay guys, 6.11, the types of forces guys. We must know that we have what we call bending stress, direct stress, whereby we have again shear stress. All right, we have many types of stresses guys. We have many types of stresses. Can see we have what we call bending stress, we have what we call again we have shear stress, we have direct stress. So far these are the 3 types of stress: bending stress, shear stress, and direct stress. All right, this is what you're supposed to know so far. Then I've given 6.2 says a steel rod with a length of 250 millimeter and diameter of 200 millimeter is compressed. There is compressed on the both end by force and became 0.2 millimeter shorter in length. You see, this is the change in length. Calculate the magnitude of the compressive force. Take young modulus of elasticity to be 80 gigapascal. So all right, what do we have then? I can write the data for us. We have the length there. The length there is 350 millimeter. We have the diameter, which is 20 millimeter. We have the change in length there we've given, which is 0.2 millimeter. So they say we should calculate the compressive force. You want the magnitude of the force. So I can quickly grab our information here. Let me just copy it like this, then I will write it below. All right, so this is what we have. So let us find this. Let me write it here on the, let me paste it here on the, all right, this is what we have guys there. So that is what we have. We want the force guys. We've given this, given the diameter. This is what we want, the force. All right, so we don't have the shear stress. All right, so since you have given the shear length, this here is the formula that you might need to know. There's this formula that says the change in length is equal to force multiplied by the original length, right, divided by by the area multiplied by young modulus. This is the formula you're supposed to know. So using this formula, we want the force. We can make the force the subject. If you make the force, you multiply that side, will be change in length multiplied by A. All right, but by area multiplied by young modulus divided by L. If you divide this by the length, you'll have your force. So therefore, a formula for calculating force, as you have seen there, will be area. Here we have our area multiplied by Young modulus, multiplied by the change in length, divided by the original length. So we want the force. All right. The area, guys, is given by pi over 4d squared, right? So multiply by E, multiply by the change in length, divided by the original length. So if we substitute this, pi will have pi over 4. Our diameter there is in millimeter. Divide this by 1000. You'll have this to become 0.02 meter. This is the same as 0.02. Then we have to square that, multiply by Young modulus. Young modulus of elasticity, we did not take that. I'm sure we're given there 8 gigapascal. It's 80 there. So we have our Young modulus, which is what it's 8. Young modulus, we multiply this by 80 times 10 to the power 4 of 9. The change in length, here it is, that is 0.2. Convert this to be meter, multiply by 10 to the power of minus 3, will be 0.2 times 10 to the power of minus 3. Then we divide this by the original length, which is 350. This is the same as 0.35, right? So we punch this on our calculator. Let me try and grab mine and see what we'll have as our force. Remember, this is simply just our force. If we punch that, let me grab my calculator quickly. You have, okay, we have there pi over 4 into 0.02 squared, multiplied by multiply this by 80 times 10 to the power of 9. Remember that is gigapascal. Then multiply this by 0.2 times 10 to the power of minus 3. You're converting this, when multiplied by that, we're converting this to be in meter. Then all right, .2. Okay, I'm just punching this, divide by 0.35. Okay, what is the force there? I will have this to be 14361,566. This is measured in Newton. Obvious is the force 66 like this. So if you want this to be in kilonewtons, it is up to you. You can divide that by 1000. If you want this to be in kilonewton, you divide this by 1000. If you want your force to be in kilonewton, you divide this by 1000. The answer you have, you can divide it by 1000. We'll have 14,362 kilonewton. This is what we have there. All right, we have the force now that I said we should calculate compressive force. Then here 6.3 says the following result we obtained by means of a tensile test on a carbon steel. The L like this, if you have a dot, this means is the original initial length. It is 6 millimeter. All right, then dot like this, initial diameter is 40 millimeter. Then this is a change in length, which is 0.055 millimeter. We're at the limiting proportion. Then the force at the limiting proportion, it is 90. The force at the limiting proportion, I'll just say F lit like this. Limiting proportion will be 98 kilonewtons. Then the load at the yield point there, force at the yield is simply 110 kilonewtons. So far this is what we have. So question 6.31 says calculate the following: the stress at the limiting what proportion, the stress at the limiting proportion, the stress at the limiting proportion. What do we have there? The stress at the limiting proportion. This is what is this? It's 6.3 point. This you have 6.3.1. The stress there at the limiting proportion. So far, we know that the stress is equals to force divided by area. You must know that the stress is equals to force divided by area. So this is the information that we are given. All right, this is the information that we are given. According to that information, when the force at the limiting proportion, we must use the, if we want that, we must use what we call the force at the limiting proportion. Remember, when the stress at the limiting proportion, we must use the force at the limiting proportion. The force at the limiting proportion, I said, is 98 kilonewton. This is times 10 to the power of what? Of 3. The area, you use the original diameter. You've given the diameter there. You use your diameter there. Then diameter, its area is pi over 4. Then you know is d squared, which is 0.055. Remember, this is in meter, must become in millimeter. Multiply this by 10 power of minus 3. Then you square these guys. Then let us punch this and check what we will have there. All right, what will be our value there? All right, what is the answer there? Let me punch 98 times 10. 98 times 10 to the power of 3, isn't it? Divide this by pi over 4 into 0.055 times 10 to the power of minus 3. Then I square this guy. Then I will have 4 comma, let me just reduce a bit. Yeah. Oh, this will be huge. Oh, this is very huge, but then there's no problem. Since it is huge like this, I can reduce it a bit. Okay, let me reduce to gigapascal, or let me reduce it to gigapascal. All right, this will be 41248 there, 41248 comma 75. We have 2 watts, must be gigapascal. Remember, this is the same as times 10 to the power of what of 9. If you replace that with, must be in gigapascal, I replace that with the G there. So this is simply in gigapascal. That is our stress. Here is very big. It's a huge value there. All right, we have that stress in limiting proportion. Then the the modulus of elasticity of the test piece. Check the modulus of elasticity of the test piece. We know that will be stress over what? Over strain. Remember, the strain is equal to change in length over original length. This, we call this the what? Young modulus of elasticity or strain. This is a strain. All right, this is a strain. So Young modulus is equal to stress. We have our stress there, which is 4.1. Then 48,752 times 10 to the power of what? of 9 divided by Young modulus divided by the strain, which is a change in length over original length. So what is our change in length here? We have our change in length to be what is changing? 0.55. Okay, this is in, so substitute, you can substitute them directly. Both of them, they are in millimeter, so there's no problem there, guys. Both of them, which, remember, the strain is what is a change in length, or let me just do it here on the side so that you'll understand. We know that strain is equal to change in length over original length, then that is 0.055, right, divided by 60. Why? Is because this is in millimeter, also this is in millimeter, so even if you don't change those units, those SI units will cancel. As you can see, guys, this is the original length is 60 millimeter, this is 0.055 millimeter. If I divide this with the same SI unit, it will simply just cancel. So I can simply take all of these there at the bottom. Remember, this is here. So if I substitute that there, you may see that I will have, this will be 0.055 divided by 60, like this. Then we want our Young modulus of elasticity. And then what will be the Young modulus of elasticity here? Let's check our Young modulus of elasticity. I punch this on my calculator. Then I will have 41248,752 times 10 to the power of minus 9, like that. Divide this to 0.055 divided by 60. Let's check. Go. This fail is too much, guys. Let me double check something here. This fail is so too much. Let me double check here, guys. Okay, I did mistake here, guys. Sorry about that. Remember, here it's a force. It's 14. Sorry, guys. Here it's our force. This 98. I got it to this 98. Or here it's our 98. Force at the limiting. The stress at the limiting proportion here is 98 kilonewton. Divided by the. There is a diameter. It's 40. It's not 60, guys. I made a mistake. This is a length. Oh, guys, this is 40. There is a mistake that I did. I did the mistake. Why this thing so big? Sorry, guys. Here, okay, the force is right. Pi. Now the diameter. This was the length, guys. Oh, I made a mistake. This is the length. Supposed to use this 40. Oh, sorry, guys. The diameter, as you can see there. I was amazed why I get this. This is our diameter, guys. It's 40. I've used this. Okay, sorry about that, guys. It's 40 millimeter. All right, so I will need to adjust all of here from here. This is the length. Is supposed to be 40. Right here we have the 40 divided by 1000. There we'll have this to become 0.04. Then let us check now and punch. Obviously this will be wrong. It's very big. I was amazed why I'm getting such a value. So I have 98 times 10 to the power of 3. So what about these guys? So it is advisable to double check your work. You see now here, now we're talking, this stress will be 70. Now we're talking, this stress will simply equals to 77 here, 77,986, which is, this is what it's in megapascal. Now this is making sense. then okay, this here, okay, this is right. So what I have to adjust here is here. The stress now is wrong. Must use the one that we got. Okay, let me just do like this. Okay, all right. Here we still have a young modulus. The stress now is the one that we got, which is 77,986 times 10 to the power 4 of 6, like this, divide by that, which is 0,055. Okay, divide by 60. All right, so let me punch this. You see, now at least maybe I will get something that makes sense, something that which makes sense, guys, not that folks that I got 98.6 times 10 to the power of 6 divided by now 0,055 divided by 60. All right, this makes sense. Yeah, yo, this now young modulus, our young modulus will simply equals to 85 comma 0.76, which is, this is in gigapascal. This now makes sense. This is our young modulus. It's E. All right, let me write it so that you'll see. This is our young modulus. So this is what we have so far, guys, and thank you for watching. And may you please may you kindly subscribe to my YouTube channel and click the notification button so that you'll be notified whenever I post a new video, guys. Feel free to like and share this to your fellow classmate, right? All right, all the best, guys. See you in the next comment session.